Good. For today, we are in class. Here we go. AI tools, January 23. This is our class today. We have two more classes, okay? And I want to clarify. I'm going to send an email about this, but this class and this one is going to take place presentially, okay? No more online classes. Today is the last online class. Next, we have a theoretical lecture with one external guest that is coming with us to talk about this topic that I pop up last week about authorship with using AI tools, about digital culture. Okay, we are gonna be discussing about this during the class. So this will be in presence. Okay, and then last class, parametric field. We have only this class. We are going to produce nothing. We are going to join all of us, and I am going to explain in detail how you have to do the final submission. Okay, we will go step by step through our grasshopper definition, organizing everything that we have done until now, and explaining what are the requested parameters that you should change. Okay, some of them are specified, other ones you have to choose them. Okay. Well, just for you to know, I think that I say it. Some students didn't know it. I uploaded during Christmas. I uploaded some extra content into Ilias. Okay, so you can have a look. There are books, YouTube channels, there are websites that you can follow a structured course. There are a lot of resources that I think that they will be interesting for you. Okay, but let's gonna talk today about evolutionary algorithms. Let me do one small recap here. This presentation, you have it already on the Ilias course. What we have done till now, as I said, was kind of symbolic AI. It's kind of automation. You know, we have prepared some grasshopper definitions that you enter with certain geometry. You specify some parameters there, and then you have an output depending the parameters. Okay, kind of like this. Then we have shared time planning and evolutionary computation. Shared time planning, we haven't done it because this will be like a loop, sometimes called a for loop or while loop, okay, in programming language. And then we have evolutionary computation. This is what we are going to do today. Again, evolutionary computation is how to find a solution like search and planning, testing a lot of possible solutions, a lot of possible options for this solution, but let's say in a smart way. Okay? Let's going to try to understand a bit what is behind this smart way today. Charles Darwin and Gregor Mendel, of course, they didn't invent evolutionary computation, but what they don't know is that those two guys, Alan Turing and John Henry Holland, they invented evolutionary computation. They were based on those principles. What are those principles? The principle is the theory of Darwin of natural selection serves as the central model for evolutionary algorithms. What they took from his principle is survival of the fittest. In each generation, the fittest individual, fittest mean the one that served the best for one solution, for one solution. For example, the highest, the tallest, okay, the smallest, the fastest, okay. The most are selected for reproduction, okay. Only the fittest elements, the fittest this is called genomes in a generation, are the ones which are selected for reproduction to pass for the next generation. The rest die. Okay? Genetic variation is not only about selecting the best ones. Okay? It's also about how these best ones are populated, are let's say, are joined with other ones. Okay? Mutation and crossover processes in the algorithm emulate the genetic variability Darwin identified as essential for evolution. Maybe one of the fittest one in the previous generation joined with one of the bad ones of the next one. Okay? But the output of these two genomes doesn't have to be a bad genome again. Okay? There is certain crossover and mutation algorithms applied there. And maybe you have a very good genome joining those two, okay? And then adaptation to environment. This also affects, it's not only about how you were born, it's also how you adapt to your external conditions, okay? I just explain this in very plain language and don't get into complex terms, okay? The algorithm search for solutions that best fit the problem, similar to how organisms adapt to their environments. For example, we have the giraffe here, that the neck of the giraffe, every population is growing because he needs to eat whatever is in the tree, the leaves or whatever, okay? And this is adapted through different generations because of the environment. The reason is the external conditions. Okay, so this also affects how the population is evolving, not only how they, let's say, join between themselves. Okay, happens the same with birds. Okay, they have different endings. The birds, depending what is for example, what is the fruits that they are eating, the insects that they are eating, or whatever other reasons. Okay, but this is also the result of this depends on the environment, not how we populate those genomes. Okay, this is so the principles of natural selection is that variations exist in a population. This is what we said. Okay, it's not only the best one are the ones that are going to pass through the next generation, are the ones which are going to be populated between each other. It's not like this. Okay. More offspring are produced that can survive. This is very important. We need a very big amount of data. We need a very big amount of genomes in one series to be able to find a good solution. Okay. Individuals with advantageous traits have higher survival and reproduction rates. If you are good in one topic, it's very likely you will survive and reproduce yourself, okay? These traits are passed on to subsequent generation. Your features are transmitted to the next generation, okay? Over time, the population evolves to become better adapted to its environment. And this is also something that we were discussing before, right? The environment affect also the final output. So guys, all these principles are embedded into one grasshopper component, okay, that we are going to explain very shortly. But not only Charles Darwin, also Gregor Mendel. Gregor Mendel was use of how the data is going to be, let's say, merged, okay? While Darwin provided the framework for evolution, Mendel explained the mechanism of genetic inheritance, which are also key in evolutionary algorithms. We have genomes and chromosomes, genetic crossover, and mutation. Genomes and chromosomes, possible solutions are often represented as chromosomes with genes encoding specific characteristics. You, as an individual, you are something that is called a chromosome, okay? And inside you have genes that represent your features, okay? Genetic crossover. The recombination of genes during crossover in the algorithm is directly inspired by Mendel's principle of segregation and genetic recombination. Genes, I mean, genes are very complex to understand how they are recombined or merged together. Okay, so you remember? I think that you have studied this in the school, right? This is how seeds, if you have two seeds, how they merge together, and the different population, if we have those seeds, what we can obtain at the end. Depending on how these chromosomes, depending how these genes are merged. Okay, so those were the principles that Mendel discovered and are adapted for computational design. Who adapted this thing? Alan Turing and Jerry Henry Holland. Alan Turing, I really recommend you to. I was reading a book these holidays about Alan Turing, actually. His life was crazy, but really crazy. He's very interesting person, really, really interesting. He has really cool, he has not really cool things. While Turing did not explicitly develop evolution algorithms, his pioneering work on computation, natural selection, and biological pattern formation profoundly influenced the theoretical and conceptual foundations upon which evolutionary algorithms were later built. Those are the fathers. He developed the principles, and then John Henry Holland is the one who finally developed the evolutionary algorithm topic. Okay. Alan Turing, for example, did a machine. Alan Turing machine. You can. I suggest you to have a look in Wikipedia. This is really, those two guys are really interesting. But well, let's go to our topic. This is the component we are going to use today. All of you should have it there. Okay. Let's gonna open Grasshopper and let's going to place it there. I hope. Well, give me 1 second. I hope that the explanation was not too abstract. I try to make it as simple as possible, but well, let's see. Okay, so let me copy paste this thing here. I have this for me to guide in case I get lost. Okay, let's gonna start placing. Double click on the grasshopper canvas, Galapagos. This thing, okay? This component. Guys, whenever you see one component that is like broken, you have it here, means that the component has no output. And Galapagos has no output. You are not going to receive any output. What Galapagos does at the end of all this history is changing number sliders. Okay? This is basically what Galapagos does. So let's going to see if you double click in Galapagos, double click here, a window pop-ups, right? Guys, are you following? I'm not reading the chat, sorry. Are you following me? All good? Galapagos, double click, everyone has Galapagos, no plugin needed to install. Yes, perfect. Let's go into stay here. I'm gonna change to this page and let's going to see what we do. Fitness. Galapagos, as you can see, it has two inputs, fitness and genome. Genome, as we were talking, are your population, okay? What do you want to test? To find the best one, And fitness is actually the value that you want to test, that you want your genome to be adapted to, okay? The fitness can be minimized or maximized. Let me open the rhino. Where is my rhino? Okay. Fitness can be maximized or minimized. Okay, you can find the minimum maximize fitness or minimize fitness. Okay, what is the threshold? Let's gonna see step by step. I am going to upload the presentation, so you don't need to take pictures, and because you are not going to find this explanation anywhere. I did it. Is honestly speaking, the editor of Galapagos is a bit let's say there is not a lot of information out there, okay, about it. So I will upload this for you to have it because I think that is a very useful tool. Threshold. What is the threshold? Threshold is the acceptable fitness value, then the simulation will stop. If you know the value that you want to achieve, you can introduce here the value. And when your fitness number will get to those value, simulation stops. Says, hey, this is good enough for you. Okay. Remember, guys, here we are not finding in evolutionary computation and machine learning, guys, this is not mathematics. I mean, it's of course mathematics, but it's not 1 + 1 = 2. Okay, there is no an easy solution. When we use evolutionary computation and machine learning means that the solution is not fully specified. Okay, you can find something that theoretically is the fittest, the best solution for one problem. Okay, can be a bit better, yes, for sure. Okay, it's difficult. We need to play the simulation a lot of time in evolutionary computation to be able to find the best solution. Okay, this is if you want to stop the threshold, the definition while you find a value. You also have runtime limit and maximum duration. You can specify a duration. I have left Galapagos running for a day, an entire day, trying to find a solution. Because when you enter here complex problems, then it takes time. Okay. Good. 1 second. Evolutionary solver. Here we go. We have two solvers: evolutionary solver or the annealing solver. Evolutionary solver is the one that we are going to use most of the cases. Annealing solver is another algorithm inside the program that simplifies the computation, let's say, process. Okay, as you can see, it only has 3 values: temperature, cooling, drift rate, and here you have 1, 2, 3, 4, 5. Okay. Evolutionary solver has 2 groups of inputs: maximum stagnant. Maximum number of stagnant, that means fixed generation before the solver aborts. What this is going to do is going to populate different generations. I mean, creating different configuration between your genomes. Okay. When 50 generations are passed and the final output is not improved, okay, then we say to Galapagos to stop running the simulation. That's why I told you this doesn't mean that we have found the best solution. That means that this solution is the best that we could find. Okay. Population, number of individuals per generation. This means 50 means that whenever values you introduce into genome are going to be merged to generate 50 genomes, 50, how was the name? Sorry, it's not genome. Wait a second, I forgot the word. Chromosomes, okay? It's going to generate 50 chromosomes per generation, okay? And the initial boost. Initial boost is important because the first generation that we run this to avoid problems, we should have a big amount of chromosomes, okay? Of, let's say, how we can call this easier, of guys, or, or we should have a bigger number of items, okay? So in case that you run a simulation and it doesn't work at the beginning, you know what it is, because you need to increase initial boost. You need to give a bigger population at the beginning, because sometimes this happens. You run this and the simulation doesn't work, the first one. So you need to change the initial boost. Or for example, the Galapagos is not able to find a solution. So you need to increase For example, the number of stagnant generations, or decrease it, because then you don't need so many. We are going to see it, okay? By the way, if you do right mouse button in those values, in maximum stagnant, in population, initial boost, you have default values. And the names are really, let's say, descriptive, okay? They describe very well what the value is aimed for, Let's go to see it later when I open right now, show you. Then maintain and inbreeding. Maintain and inbreeding means how the next population is going to be developed. We are going to maintain only the fifth percent of individuals that are better, and inbreeding is how individuals will couple per generation. Let me open 1 second and you will understand. If I click on right mouse button, hey, why is it not working? In breeding, if I click right mouse button, ideal genome, and if you leave the mouse here, you can see also a description. Genomes pick mates that are not too different, not too similar. Usually 75% is the good one. But for complex problems, sometimes you need to go to borderline or things like this. Genome picks mates that are fairly different, used when the fitness landscape is rough. Okay, when your fitness is difficult to find a solution, you need to go to borderline, questionable. Genome picks mates on the far end of the spectrum. I am going to make one genome that is very good, one genome that is really bad, because maybe in between I find the solution. I find the best value. Okay, and also here maximum standard stagnant. You can see what does it mean. Local maxima, obvious solution. All these are kind of technical elements. You have also the blog post. I eat bugs for breakfast is called. This is kind of a nerd joke because bugs doesn't mean bugs insect. It means bugs of programming. When the program has a problem, it doesn't work. It has a bug. It's called a bug. So this kind of like I eat bug for breakfast. And this blog post is developed by the developer of Grasshopper. He's an architect, David Ratten. Okay, you can have a look. There are really, from here is where I got the information. Not all the information is there. You're not going to find everything there. Okay, but something, yes. Okay, this is the first graph of Galapagos. The second one is, if you click on solvers, okay, is this one. You are not going to see it like me because you are not running a simulation, okay? On the top, we have the generation graph. This shows us how the generation is running. Here you have generation 0, 1, 2, 3, 4, 5, 6, and those are the values, okay? The values that it found, okay, in this generation. This is the best value for every case. On the bottom, you have, for the selected generation, you can select one generation or multiple generations. You have the genome map. How was the genome of this generation? So we have the ones which are with, you have two options here, no? A dot and a cross. The dot means that this generation, this genome is going to pass to the next generation, and the cross means that it's going to be killed. Okay, it's not going to pass. And this is the spectrum of values. You can see that we have one very different value here. This is the number slider value representation. Those vertical lines are the number sliders which are connected to the Galapagos editor. So in this case, I have 1, 2, and 3 number sliders connected here. Okay. Then this spectrum, this hatch area here with purple are the spectrum of values that our number slider have been they have achieved, let's say, okay? And this is the genome representation, okay? The best value here is 6029. Okay, so that means that I am trying to minimize, for example, I'm trying to minimize an area. Okay, so this is the fittest one. You see, 6029, whatever value. I don't know what was that, to be honest. I don't remember. The generation, well, I then explain one by one, little by little. The generation graph, you can see the number of the generation. The software will stop after achieving no improvement in the best genome after the specified max stagnant value. You remember this value from here, right? Whenever we achieve 50 generation, for example, with no improvement, then the value will stop, okay? This has like different hatches, okay? Because the red line is the average fitness value. This is normal, okay? The normal value for your solution. The ones which are below are the weakest, and the ones which are over or going down in this case, let me see if I can, yeah, those ones are the strongest one. So this is the best, this is the worst. Because this line, this vertical line is the fitness value, okay? Understood this one? And these marks here, you will see some marks at the top, means that one individual in generation X is fitter than the fittest individual for generation X minus 1, which means that in this generation, this was an improvement from the previous one. Okay? Whenever there is an improvement, we have these marks. Then the genome map, genome that is not fit enough, genome that fits to the next generation. This I already explained you. Number slider value representation. Those are the number. What I told you before is this. Okay, this is the max value, minimum value. Okay, and then the genome coalescent representation. When two mating genomes, Galapagos needs to decide what value to assign to the genes of the offspring. We have this genome is, let's say, this is a bit weird because they use very specific term couple. This genome couples with this other one, and we have different outputs depending the algorithm that they are using to couple those genomes. Okay. When we were selecting, guys, when we were selecting here the inbreeding, okay, how the genomes are going to mate with genomes in the same generation for the next one, what it means is this. I think that here you can understand it better. We have the genome map, okay? Incestuous mating means limit your search of potential partners to your immediate neighborhood. That means that you mate with individuals who you are very much like you, and it means your offspring will also be very much like you. Low diversity decreases the chances of finding alternate solution bases, and thus it risks getting stuck in local optima. This is not a good incestuous mating is not a good process when your solution, your fitness is complex to find. Okay. For example, incestuous mating, we are going to do 2 exercises. Will be okay if we are finding the minimum bounding box for a cone, for example. This is easy. Okay, but what is not easy will be the second one. That is going to find. We are going to give a plot, okay, to our building, and we are going to find the maximum area of a building that we can build in this plot. Okay, this is not easy. And this has a lot of options. So for this one, we will use zoophilic or kind of more option than incestus. But you know, I hope that you have understand this. If you don't understand something, please let me know, because honestly, this is a bit tricky to explain in architecture field. Zoophilic mating. The other extreme is to exclude everyone near you. Okay, you will often hear it said that opposites attract, but that's true only up to a point. At some point, the genomes at the other end of the scale become so different as to be incompatible. Okay, so the genome is going to couple with those ones which are far away from him. Okay, far away in characteristics. Okay, and at the end, this is what we have. Okay, merging those two, we have an intermediate that is usually where we try. Don't select the one which are very far away. Don't select the one that are very close to you. Select some of them that are kind of in between, are not super similar to you and are not very different to you. So you can couple with them and then find a diverse solution, different solutions. Okay, guys, understood? This part, this was like the theory a little bit for you to understand what is going on. Now we are going to practice. Okay, let's go. Let's go to Rhino. Okay, you have already placed your Galapagos component, right? Okay, so let's going to do our first exercise. Is going to be, this is my plot, for example, I draw here. The first exercise is going to be, hey, why I do have like duplicated buildings here? I'm going to delete them. But then I have this one. I'm going to open a little bit of a space here. 1 second. Let's going to place here a cone. So for this cone is the command. I place it here, kind of like this. Imagine that, I don't know. This is, I mean, we are doing in the building scale, but it's not going to be a building. Okay, so we do a cone, just for practicing. Let's going to rotate the cone 2 times, like this. Okay, I don't know, or more dramatic. Let's going to put it, I don't know, something like this. Okay, and then I want to rotate it a bit like this, something like this. Okay, this is going to be my cone. So this is a very common exercise when we are working with data fabrication, which is I need to buy a piece of wood and I'm going to mill with a robotic arm this code. Imagine that this code is, I don't know, this cone is smaller, is, I don't know, like 20 centimeters. Okay, the size doesn't matter at this time. This is just a simple example for you to understand Galapagos, okay? So let's go there. For this, we need to use the bounding box component, okay? A bounding box component has 2 inputs, the content and the plane where we want to generate our bounding box, okay? The content is easy, right? We put a geometry component, geometry, and we select the cone. So the cone is this one, okay? And I put it here. And then this generates the bounding box. Bounding box is the minimum box that contains the element, okay? Okay, guys? It's clear? Yes? No?
It's clear, yes.
It's clear. Okay, okay, good, good. So, so now the thing that we are going to do is we are going to generate different plane orientations, okay? We are going to generate an XY plane, but we are going to rotate this plane in the space, okay? To adapt this bounding box into different areas, okay? For this, we need to do it with the rotate 3D component, okay? And the rotate 3D component, we are just going to rotate 3 axes, X, Y, and Z, okay? Now, let's going to introduce here the axes. You need X into the X, because this is the axis. You need Y into the axis, and you need Z into the axis, okay? And then we connect 3 number sliders that go from 0 or 0.00 is smaller than 360, because this will be a full rotation, okay? This is the angle, from 0 to 360. But guys, for the angle, remember, Grasshopper always use radians as angles, okay? So in the angle input, I need to do right mouse button, degrees, okay? Right mouse button, degrees, right mouse button, degrees. Copy paste these things 3 times. And here 1, here 2, here 3. Okay, so we have those 3 angles. What we want to do is change this plane depending this orientation. Okay, that we are going to generate here with these 3 number sliders. Okay, so for this, I am going to do a transform component. Okay, what I'm going to transform this plane, and the transformation is going to be those 3 together. Okay, so for this, I need to use a compound. It's called compound 2 transformations. You can compound multiple ones. You can compound, I mean, the transformation is this one. Okay, this one, then press shift to add another one here, then press shift to add another one here. I will have the compound transformation that we connect here. So we have, you see, we are moving this plane in the space, okay, in the X, in the Y, and in Z, okay. This transformation is what this plane, this geometry, is what we're going to introduce here. So at the end, we can rotate the bounding box, you see, that we have generated. All of them are bounding boxes for the cone. But if I go to the store, to the shop, and I buy this amount of wood, will be more expensive than if I buy this one, right? Because, I mean, this is smaller. Okay? So what we want is optimize the volume of your bounding box. Okay? So out of this bounding box, out of this one, I'm going to calculate the volume. I have this volume here. This is a number. I'm going to place a number. Okay. And this number is what I want to optimize. This has to be like this. You will see why, because I need to connect Galapagos with this thing and with my 3 number sliders. Okay. I'm going to place a panel also to see the value. Right now is 31,000 cubic meters. Okay, because this is a huge thing. So let's go to connect things. Let's go to start placing the fitness. Okay, to place the fitness, guys, you need to click here with left mouse button and then come here and you'll see that it will be linked. Okay, it's a bit different to what we have done now. Okay. okay, with grasshopper. Okay, good. And what is my genome? My genome are my three number sliders. So I'm going to connect my genome with my three number sliders. There is one way to do it, that if you select the three number sliders and then you select Galapagos, you can do right mouse button, select all sliders. And you don't have to go one by one. You see? Good? It's okay, guys? Here with me?
Yes, it worked.
Okay, it worked. Nice. So now, double click. Okay. Let's just start preparing the solver. What do we want to do? Maximize or minimize the volume? First of all, we want to minimize the volume, right? Good. Maximum standard. In this case, this is a super simple solution. We don't need to touch it. Let's gonna just play, I think, and let's gonna see how it works. You go to solvers, okay? In solvers, you have on the top, you have the evolutionary solver or the annealing, simulated annealing solver. You see, you can change from one to each other. Solution is the same, but this one is easier. Everyone use evolutionary solver, okay? Here are the, what do you want to display in the Rhino viewport? Display all genomes in the Rhino viewport, so then the performance will be slower, or do not display any genomes, so that the performance will be faster, but you will see nothing in Rhino. You will see nothing, okay? I'm gonna click here, display all genomes, and this is an easy, problem. And then let's click on a star solver. I see nothing because I haven't selected anything in Grasshopper. So done. 17126, which is this value. Okay? Then click OK, and we are done. This seems the minimum bounding box that we can have for this item, which seems correct because this face is kind of containing this one and then goes here. Okay, maybe you found, I mean, we don't have here the same value because we have for sure different elements, but this is kind of the minimum one. Okay, let me go here again. Let's gonna click. If I click here again, it will be a bit weird because, let me 1 second. I need to click on the bounding box, and for this is important to start playing with the visualization. I'm gonna click here, draw a contour to display my bounding box. And I'm going to rotate it again. I'm going to rotate it like this, okay? So I can see what is going on. If I double click here again, I'm gonna just click on a star solver and display genomes. You can see that the best genomes are displayed, and it's trying to find a solution. Again, solution found. 17, maybe now the solution is better than before. 17127, this is the fittest one. You see, if you go here in this graph with the right mouse button, you can see the graph, different generations, and you can select one generation to see the values. Okay. And you can see how the different generations change. Here I will have 50 because I have select 50 generations. Okay. If I am interested specifically in one of them, I only click on reinstate, but the problem is that I will lose the best one. You know, if you move up and down while you are clicking the right mouse button, you can increase or modify the scale of your graph. Okay. Okay, guys, did it work for you also? Did you find a solution? Let's go to see what happens, for example, if instead of 50, I have here 10. Number of individuals per generation. This is, right, Mobroton, this is a very small, this is a very small population. You see that you have XS, S, M, L, XL, Mississippi. I don't know why it's called Mississippi 200, to be honest. Okay, then click OK. Oh, sorry. Then I'm just going to see what happened. Just gonna click on Star Solver. I'm gonna display the solution. Yeah, solve it. You see? This was an easy problem. If I click here, I display nothing. You see the cube is not moving at all. And this means about, well, you can see Galapagos, the version, when it was developed, 2011, 21st of August, 2011, guys. They have more than 10 years. And still, a lot of people is using Galapagos. It's really a useful tool. Okay, well, now people are starting to use Galapagos. Good, understood this one? This is the easy example. I'm gonna move it here. Understood, guys? No problem with this?
Yes, no problem.
All good. Let's going to do another example that is going to be a bit more difficult, okay? But let's going to see how we work with Galapagos, okay? We are going to do 2 plots, okay? And we are going to generate. Okay, so the first thing that we need to do, we're going to hide this one. Let's gonna go into a view top. Let's going to draw a plot. Imagine that my plot is something like this. I have this plot here, but suddenly here I have, I don't know, I have an issue that I cannot build anything here, and then it's like this, and then it's like this. But here again, I cannot build, so I have a very complex plot, and then I close it. Okay, I have a complex thing, something like this. Okay, or I think, wait a second, I think that I already draw my plot. Where it is? This one. Yeah, well, very similar. I imagine that I can't build in this area, no? Good. So I'm going to put in my plot with geometry component, set one geometry. I'm going to select my plot. Okay, here we have it. So now we are going to generate inside my plot rectangles or cubes or that are my building plot. Okay, so this is not my building plot, it's the size of my building actually. Sorry. So for this, how I'm going to do it, there is one component in Grasshopper which is rectangle 3 points. Rectangle 3 point. This one, rectangle 3 point, and I'm going to use this one to generate the size of my building. I need to introduce 3 points here. So let's gonna start putting the points, okay? The first one, we are going to find it with evaluate curve, okay? With evaluate curve, I can find the first point. My curve is going to be my plot, okay? But this is very important, guys. Right mouse button in C and select reparameterize. Okay. And now we are going to generate a number slider that goes, and this is important also to put a lot of digits, 0.1, 2, 3, 4. I'm gonna put 5 digits, 0.00000, because this is an option smaller than 1. Okay, it's important to put a lot of zeros because these are 359 genomes. Okay, so now I have more genomes in my population. Okay, I can have more values. And I'm going to click this one here. And this is just finding a point that goes from 0 to 1. Okay, 0 and 1 are because it's a closed curve. Okay, so this point is going to be my first one, the A, okay? It's going to connect it here. And still, I don't have the rectangle. We need 2 more points. Good. How we are going to find the second point? The second point, what we are going to do is we are going to project this point into my plot, again, following one direction, okay? So for this, I use project point, okay? And I project this point into this geometry, okay? Opa. Okay, well, and then in what direction? This is the question, right? Let me 1 second. I'm gonna change the chat here, okay, and make it bigger. Yeah, here we go. If you're writing something, I think I can read it, okay? And then the projection direction. So for this, what I'm going to do is very similar before. I'm going to rotate, but rotate this one, rotate a vector around an axis, okay? The vector that I'm going to rotate is the unit x vector, okay? I'm going to rotate a horizontal vector around the z vector, unit z, okay? Unit z, and then I need to provide the rotation angle, okay? That, remember, we are going to provide it in grades. So in degrees, sorry. So it has to be degrees, okay? So it goes from 0.00000 smaller than 360, okay? Here we go. And then what I will do is project this point in this direction. This is maybe red and is fine because means that there is no projection in this direction of the point. Okay, now you find the direction. You see? So this is fine. There will be some solutions that is no solution. Other one, there is a solution. Okay, because I can project this point in the x direction, I can project it. And until I find a possible solution, here we go. This is one. Okay. Okay, so this point is going to be point number B. Are you following me, guys? I'm gonna try to organize this. This is going to be point 1. Okay. Point 1. Here I have point 2. You with me?
I'm sorry, what is the start geometry?
Sorry?
What is the start geometry we are using in this?
The geometry that we are using, this one,
yes.
Is the plot, Julian.
Okay.
Is my plot. I'm going to modify my plot, by the way. I'm going to make it a bit bigger. I'm going to adapt it here because I have made bigger. Okay, so is the plot, whatever you wanna input. I mean, later we can modify the plot and see if we find a solution with Galapagos. Maybe not, okay? But yeah. And now, I mean, you will see, guys, that the complex part here is not Galapagos, is define the problem that we are going to do now. This is the complex thing. So now we can generate, for example, the first line of our rectangle. Okay, we can generate our first line that goes from point 1 to point 2. Okay, so this is the first line of my building. Maybe my building is like this. Okay, the biggest one. Let's see how we do it. Then how to find the third point? The third one, what we are going to do is, based on this line, okay, we are going to put a perpendicular frame to it. Perp frame, a perpendicular frame, okay, to this line. So this is my line, okay, and again, I need to reparameterize. If I reparameterize the line, guys, remember that my line will go from 0 to 1. If I don't reparameterize, I don't know the t values. I don't know it. Okay, t is the parameter on curve domain to evaluate my line. Okay, so now my line is going from 0.000 smaller than 1. Okay, like this. I'm gonna put it here. And then I have a plane that goes from the beginning to the end of my line, okay? How to find the point number 3? I'm going to use this plane, okay? And I am going to deconstruct the plane. Deconstruct the plane. And then I have the origin, X, Y, and Z. I'm going to use the Y, how is it called? The Y vector, sorry, okay? And with the Y vector, I'm going to multiply, no, it's not, it's multiplication. I'm going to multiply my Y vector, the Y, okay, with a number. The number is going to be -1 or 1. So I want to use the direction of the vector in one direction or the other. Okay, so I have these two options. Okay, so for this, I'm going to do a panel -1. Okay, now take care here, guys. Double click in the panel, press enter, 1, click outside, -1, 1. But I also do right mouse button, click on multi-line data. Okay, so now I have a list of 2 items, -1 or 1. Okay, what I'm going to do is I'm going to put a list item here. And on the I am going to introduce 0, smaller than 1, a number slider that goes from 0 to 1. I have 2 options, or 0 or 1, one direction or the other one. You know, so at the end, I'm going to multiply these values. So I will have one vector or the opposite. One vector or the opposite. All of these, guys, to find the point number 3. But wait a second, because we haven't finished yet. I have now the projection direction, okay? But what I want to do, let me 1 second. Let's going to organize this. I have the line, perpendicular frames. Well, let's see. This is the projection direction, okay? Like this. And yeah, let's going to keep it like this. What I'm going to do is to find the third point, I am going to project point number 1, point number 2, and this one here is going to be point number 3, point 3, I mean, this is 0.3, how can we call it? Auxiliary. Auxiliary 0.3. Okay? Because it's not 0.3, you will see why. Auxiliary 0.3. This one. Okay? Because to find the real 0.3, what we are going to do is we are going to project point again. Okay? And we are going to project the point number 1, which I am going to put a point component. I'm going to connect it here, and I'm going to do right mouse button and say point 1, click on the bucket, bring this one here. I'm going to do the same with point number 2. That was this one, another point component. I'm gonna connect it here, bring it here. This is point 2. Point 2, click on the bucket. And then I'm going to do the same with point number 3, that is this one. Point component, connect this one here, and bring it here. Point 3. Point 3. Okay, point 1, point 2, point 3. 1, 2, and 3. To find the point number 3, auxiliary point 3. Auxiliary point 3. Okay. To find the real point, what I'm going to do is I'm going to project the point, each one, again to my plot. Okay, so I have the point 1, that is the one that I'm going to project. Point number 2, that is the one that I'm going to project, and auxiliary point 3, that is the one that I'm going to project. In which direction? In the vector. This is my vector. This one, and this one. This is my vector of projection. To what geometry I'm going to project? To my plot. And for this, I'm going to connect here a geometry component. I'm going to rename it as plot. Bring it here. And then this is my plot. It doesn't have to be a solution. In this case, here I have a solution, not in these two. Okay. So the thing is, why I'm doing this, guys? Because I need to find the smallest distance of projection of those 3 points, and this one is the one that I'm going to consider it as my third point, the one that has the smallest distance. Okay? To find the smallest distance, how I can do it? What I have to do is use distance component and calculate the distance from each one of the points to each one of the projected points. So this point here and there, okay? The same with this one. And the same with this one. So I should have 3 distances. In this case, I don't have because there is no solution, okay? It's the first time that we are doing a grasshopper definition that with errors is fine, okay? We are going to use merge. And we merge the 3 options, okay? Option number 1, option number 2, and option number 3 of distances. This list is for distances, okay? And I'm going to have another list with the projected points. Projected points. Merge again. 1, 2, 3. I have point number 1. Order is very important. Point number 2, point number 3. Okay? Guys, I can't believe all of you are following me. Someone is lost?
Can you show again with what the geometry is connected?
Geometry here? Who is talking? Sorry, I don't
The
see
plot. The plot geometry.
the plot geometry is connected to the G.
Yes, and on the left side?
On the left side comes from the plot, comes from the geometry
Okay,
component
thank
where I
you.
select my plot, okay? This is why I call it plot. I leave it here. I leave it here for you to do it, and I give you a little bit of time. Somebody else, do you have questions? I know that this is very abstract today, guys, but you will see. This is working. Still, it's not finished. That's why I told you that today was important you come to class, because it's going to be a bit tricky.
Sorry.
Yeah.
I have a problem that there where we in the beginning where we do rotate a x vector around z axis, and there is an angle, and there is there should be some angle where the projection is not red, like it's there is no mistake. Yeah, here. And I can find an angle where it's okay.
Okay, no worries. So the evaluate curve is working, right, Sasha?
Yes.
You have pre-parameterized the curve, and your curve has some point. For example, put a point here, or a point where it's easy to project. Okay?
Yes, it works.
Okay, good. Then the projected point, let's going to select it, and let's going to see. For this angle, I mean, all of this has a solution, all of this has a solution for me, all of this has a solution. Very likely, when the point is going to be here, there will be no solution, you will see. You see? No solution at this point, because I cannot project it anymore. And in this spectrum, is no solution. Okay? 0 is no solution, but as soon as we start increasing the value, okay, because here what I'm doing at 99, there is a solution. What is going on here? I have the vector like this. If it's 0, this is 90, right? 99 has a solution. I can project here. From 99 to 270, maybe, I think that there will be solutions here. Let's see. You see, 250, 240, 260. You see, 273, no solution. For you, working, Sasha, or not?
Yes, I found it. Yeah. Yes, it was.
But it was a problem.
The parameter from the first one. Yes.
Okay. The parameter has to go from. Sorry, where is my definition? Has to go from 0 to 1. Okay.
Yeah. Okay. It's fine. Thank you.
It's fine. You're welcome. Guys, more questions here.
Sorry,
Yes, Kenny?
the evaluate curve in the beginning, for me it's orange, and I don't really understand why it says one parameter is outside the curve domain, results may be
Okay,
unpredictable.
because you didn't do right mouse button on reparameterize.
No, I did.
This goes from 0 to 1.
Yeah. Oh no, it doesn't.
Yeah, that's it. When it says this value,
Thank
is
you.
because you are welcome. You are putting here something that goes beyond 1. That's why we do the reparameterize, Kenny, because if we don't reparameterize, we don't know the limits of our curve. Okay?
Perfect, thanks.
Good, you're welcome.
I also have one question.
Yeah, it is.
The point 3 is connected to D plane Y on O with O. Okay.
With O, yeah, because okay, understood. It is.
Yeah. Thank you.
You are welcome. I try to explain it, guys, the best way I can, really, but it's very tough. It's really, really tough. In this case, you see, in this case, I have all points. I can project the point number 1 in the direction of my plane. So I have a projected point 1. I can project point number 2 also. The point number 2 is this one. So I have a projected point number 2 also. And I can project also auxiliary point number 3, which is this one. I can project this point also into the geometry, and it's this one. Now I have a list that is working with the 3 cases. Okay, with distances and projected points. Okay, I have the projected points here and my distances for each one of those points to my projected points. Okay, guys, clear? Can I continue? I don't want to continue if somebody has questions, because this is going to continue and it's going to be more complex and you're going to be lost. We still haven't we have not found yet we haven't found the third point.
It
We
is
haven't-
fine if some of our are red right now. You don't have to find a solution. Right?
You don't have to find a solution, Leona. You don't have to. But let's going to do it one option that all the items are not red. Let's going to see if you find it. The key, Leona, is in this point. Okay? Because if you are able to find this point and a projection like this, and you can project in all directions, like me, for example, this is my third point, and the projection direction that I am following is this one. So I am able to project all my points, 1, 2, and 3. Let's gonna see if you are able to find one solution that doesn't have errors. This is what we have to do to find the minimum area, the maximum area, sorry, that a building can have in a plot. You will see why. It's a bit convoluted, the definition is a bit complex, but I hope that at the end you will understand, because still we have to do something. Can I continue, guys? Yes? Today class will be a bit longer, okay? A bit longer, because we need to do also one thing with installing a software. We can have a look also the last day, okay? If you have any problem with the plan fit. Good.
I think you can continue.
Let's go into continue. Let's see. So we have point number 3. Let's go to see how we can calculate point number 3. What I want, guys, is I have those 3 points. I want to find the smallest one, okay? Because then will be easier, because if I find the biggest one, my building will be for sure out of the plot. Okay, I will have the biggest building, but out of the plot, and this is not possible. My building has to be inside the plot. Okay, so then what I need to do is select the smallest projected point as my third point. Okay, for this, what we are going to do is sort the list. We are going to sort the distances and the points together. This is important why your list has to be in order. And then using a list item, if I select the point number 0, I am selecting the one that is projected the closest, that has the smallest distance with its projected point. Okay. And now this point is going to be finally my third point. Okay. So I have point number 1, point number 2, which is this one, and I also have point number 2, which is this one, point number 1, point number 2, and point number 3. Okay, and I have generated the plot of my building. But you will say, well, Javi, but this is not working because this is out of the plot. Okay, and I will say, yeah, that's right. So that's why we need to implement something that is called a penalty function, okay, in optimization. Penalty function means we need to, what do we want to do? We want to calculate the biggest building in a plot. So from here, what we need to do is area from my rectangle, okay? And out of this area, this will be my number. And this is going to be my fitness landscape. This is going to be my fitness value, 732 square meters. Okay. So then I can place my my engine, the Galapagos here. Okay. And this will be my fitness. So then what I have to do, guys, penalty function is something that helps Galapagos to understand that this solution, I don't want it. I don't want a solution because Galapagos doesn't know that this is out of the plot. There is no way Galapagos can understand this. I need to help Galapagos, okay? How do I help Galapagos? I need to check if this is out of the plot. Then I need to, for example, multiply this number, this area, with a number that shows a value that doesn't make sense or is very big or very small, depending what I want. Okay. So, for example, what I'm going to do is I need my plot. Where is my plot? My plot is here. So I'm going to copy my plot. By the way, if you want to clean your definition with all this, you can do right mouse button, wire display, hidden, and start hiding parts. Okay, I'm going to hit my point 1. I'm going to hide this one, also this one. Wire display hidden, at 0.3, wire display hidden. Here we go. Opa, sorry. Where is the plot? And also my plot, I'm going to hide it. Where display? Okay. Here we go. So I have my plot. There is one component called trim with region. Trim with region. Okay. Trim with region, I can put a curve to trim. That this will be my rectangle. Okay. With what I'm going to trim it? With my plot. Okay. Then I have two values, CI and CO. CI is split curves inside the region, and CO is split curves outside the region. If my building is out of the plot, okay, I will be able to, let me see it. How can I do an example here? One second. Let's gonna change this. Let's going to change this, for example, 192. I want a building that is inside my plot, like this. If my building is completely inside my plot, here the area, there is nothing here. The list is empty, right? Because of course there are not splitted areas outside. If my building is, where is my building? Here we go. If my building is outside, okay, of the plot, then the list is not empty. It can be 1, can be 2, can be whatever number, okay? So what I'm going to do is I'm going to calculate the length of my list, okay? And say, well, if this value is equal to 0, okay? If this value is equal to 0, then I will have a false. It's not equal to 0, right? Because here, this is 1, okay? Since this is 1, this is false, I can transform this into an integer, and false into integer is 0, okay? What I can do is multiplication is called, okay? I can multiply the area of my, the fitness that I want to find with this integer, okay? And then this one will be my fitness. I am penalizing the value if it has parts out of the plot, okay? Okay, guys?
One question.
Did you follow this? Yeah, Kiara.
When I put the integer, it says the panel says 1 and not 0. Is that false or?
When you put the integer, what, sorry?
After the integer, my panel says 1 and not 0.
If it says 1, means that your, no, it's not wrong. It's fine. The thing is that, check it. One moment. Means that you are in this solution.
Okay.
1 second. You see? You are inside. Okay?
Yeah, okay, thank you.
If it is inside, the value will be 1. Okay?
I also do have one question.
Yeah.
My wire between trim and list length is red.
Your wire between what? Sorry? Between.
So yours is also red.
Mine is also red, yeah, of course, because if the list is empty, if there is no list, is, this is red, the wire, because it's empty, the list.
Okay.
That means, again, if you click in the rectangle, your rectangle is inside your plot, right?
Yes.
Yes? Okay, so that's the thing.
Okay.
What we have done, guys, is if my building, I want to find the maximum area. Okay? So if my building is inside my plot, this value is 1. If I multiply the area by 1, I have the value of the area, which the value is 199. Let me put it here. 199. Let's gonna see now what happens if my plot is outside. Like this. Then this value is 0. The list is, of course, not empty, it's working. And what happens when I multiply something by 0? That the value is 0. If I want to find the maximum area, I am giving a Galapagos a reason to avoid this solution, because this solution is 0, and I want to find the maximum area. Grasshopper, Galapagos will understand, okay, this is a very bad solution, right? Area 0? No. I should find another genome. This is not a good one. Understood?
Yes.
Good. Sorry, because this part is a bit difficult. Usually, guys, this is the most complex part in optimization. Find a way to make Galapagos to make it understand that, this is not a good solution. Okay, so we have the fitness value, okay? But now we need the genomes. What are going to be my genomes? We are going to have 4 integers, okay, guys? 4 integers. Let's gonna click on them together very slow, and please, all of you, follow me. The first integer is going to be the evaluate curve, okay? The second integer, press shift, the second integer is going to be the rotate. The third integer is going to be the parameter that we are going to find in the curve. And the fourth integer is going to be the projection direction, the 0 or -1. It's not integer, sorry, number slider. Okay, 1, 2, 3, 4. Those 4. Then I go to my Galapagos, right mouse button, selected sliders. Is going to be my genome. 1, 2, 3, and 4. Okay. Is this clear? All clear? I have a text here. Give me a second that I'm gonna write. Okay, I have it here. Yeah, I remember that I have somewhere. I'm gonna put this text here for you to understand. This part, what it's doing is what we said before, right? Test if the rectangle is inside my plot. For this, I'm going to find if the rectangle has intersection and penalize it, multiply with the area. So since I want the max, this is the penalty function. If it is inside this value, will be 1. So I will add another area value to the total value. Well, this I don't understand, to be honest. I brought it, this thing, but in my notes, the max area. I think that this is the clear enough. Okay, I'm going to group all this. And here we go. Let's gonna click on Galapagos. So now, what do we want to do? Maximize, okay? This is the first thing. Maximum stagnant. Let's going to do it relax, okay? 100 of maximum stagnant, okay? I want 100 generation before the solver aborts, because this is a complex problem, okay? The population per generation, let's going to increase it. Let's going to excel. Let's going to have a big population. And the initial boost is not going to be 2. It's going to be ginormous. It's going to be a big one, used in cases of many and similar local maxima. 50. I want that the initial generation may have a lot of items, a lot of genomes, okay? The inbreeding, here we go. Here says minus 100% of the inbreeding is fully zoophilic, plus 100% is fully incestuous, plus 100% means that you are mating with genomes around you, and the other one is completely the opposite. I am gonna put questionable, okay? Because I want a lot of different values. I want to try values that are very similar to me and values that are very different to me. So sometimes pick one, sometimes pick the other one, okay? Let's see, guys, maybe it doesn't work. Oh, wait a second, click OK. If you don't click on the, I want to see what is going on, okay? Let's go to see what is doing here, Grasshopper. So I'm gonna draw again a preview with the preview of Grasshopper. Okay, I'm gonna click on the green one so I always see my building. Okay, and then double click in Galapagos, solvers. Let's gonna start the solver. The options are saved. Okay, options are saved. So let's gonna start the solver and let's see what is going on here. It takes a lot of time to start. It is trying to find one. Sometimes it is going to get stuck in one solution. You will see 360, 52, 61, 64. Let's see if it's able to find the point here. Yes, here we go. It found the point. 389, we're at the moment. 393. 400. Okay, it's going. For me, works. For you guys? I mean, we are doing 380 generations, 380, 400 generations. Still is finding better options. You can also move here in Grasshopper and check the values. At the moment, this is 98, 125. This is changing. Okay, and still is finding. This is the option at the moment. I mean, you can see that we can leave this in running the whole class, and this will take some time, to be honest. But I think that we are not going to find a better solution than this. Are you running the simulation also? Is running for you? Is working?
Yes, for me it's working.
For you, is working also, Nelly? Cool. You can try many
I have
different
a
plots.
question.
Yeah.
When I start a simulation, the rectangle in my geometry turns around, but the simulation in the Galapagos field isn't showing.
Yeah, because you have, Bianca, here are the options at the top,
Yeah.
at the top right. If you display all genomes, that will display everything that it's doing. You see what it's doing now. It's testing, now it's stuck here.
Yeah.
Okay. You can click on display, only display better genomes in the Rhino viewport.
Mm-hmm.
Now we're displaying this one. Or here, do not display anything. You know, so you can see what is going on. You want to see what is going on here, you need to click here in this one. You see, and you can see all the testing that this is doing. Okay.
Thank you.
You're welcome.
I'm sorry.
Yep.
I forgot. What do the numbers mean that are on the right down corner of the
Yes, Sasha.
like simulation?
These numbers, right?
Yeah.
These numbers are the area of your building. Those are the area. This is the value. This is your fitness landscape. Okay. This is your fitness. So
yeah,
you
right.
can,
Yeah. Okay.
okay, 350 square meters is the maximum that is finding now. Since that is a bit stuck, it found the best solution is this one. But since we put the inbreeding to 0, you know, that's why it come back to this solution, which is not the best, but it's trying to find here a solution, you know? So the best solution is something like this, of course, we know it, but he doesn't. If we maybe inbreeding a little bit higher in positive direction, that will be better for this plot, because this will ease a bit the solution. This is a bug. I mean, actually, he shouldn't be searching here the biggest plot that is doing now. You know, Sasha?
Yeah. It's just I had like a big drop in the like I had higher values of area before,
Yeah,
and
me
then
too.
it dropped something like to 0 almost.
Yeah. Zero is because of this, Sasha, because it was trying to find solutions where the plot was where your building was out of the plot. This is why you have 0 here. I also have 0 for sure. Some solution, you see, some of my solutions for sure are 0 and undefined also. There is no solution. You see, but still searching. 350.
It was like more gradually, like it dropped to lower values than it was before. Like it was something like 200, like 200, and then it started to go under 100.
Totally normal, Sasha, because the inbreeding, you know, the inbreeding was 0. So that means that when inbreeding is 0, means that we are accepting also a zoophilic coupling process, which is, okay, you are here, you have found mates that are fitness, that are really good, but let's gonna also search far away from this if we find a solution. So in this case, you see, that's the problem of inbreeding, that if you put low values, it's good to find complex solution, but also when you find the solution, maybe it can get lost also. Like now, you know, now it's completely stuck. I am doing 2000. My simulation is in the 2000. Maybe this needs couple of hours to run, you know? And you will say, well, what the hell? I can find the best plot by myself, right? You can do it by hand. I mean, not really, because it depends on the plot. And really, you can draw really crazy plots and start playing here. But also, for example, this is used a lot with light simulations in Grasshopper, using plugins like Honeybee or Ladybug to find the best and optimal position of windows in a building, for example, you know? But yeah, it's a bit stuck here. You can see it, right? It found the best value for one of the slider, the best value for another one, but still this one is a bit like trying to find still, you see? It's getting a bit stuck. I'm going to stop the solver. Okay? If you stop the solver, guys, you have the best solution that was found. Okay? The best solution was 512 square meters in my case. Okay, that was the best. This was the best, and click OK, and you are done. If you are interested specifically in one option, imagine this one, I don't know. If I want to see it, I have to click on reinstate. Reinstate selected genome in Grasshopper. The problem is that you are going to lose the best one. If you click on reinstate, you see, you lose the best one.
I have a question again.
Yeah, Bianca.
By my numbers, there are no numbers, but they're standing undefined.
Sometimes this happens, Bianca. Sometimes you need to stop the simulation and run it again. Change by hand the number sliders. And then run again the simulation.
Okay.
And then open again Galapagos, run it again.
Okay, thank you.
Because you are welcome. Sometimes that's the problem, guys, that sometimes, I mean, how to explain this? We are trying to find a problem for trying to find a solution for a problem that is not explicit, you know? So this uses certain type of algorithms that sometimes can get stuck. You saw before, right? Depending on the options that I place here, these values were stuck here when we know that the best solution for sure is here. But it's not easy for the algorithm to always work perfectly. So sometimes you need to tweak, play a bit with those values. Okay, inbreeding is one key value. For example, let's going to use 20%, okay, or 30%. Let's going to put 30, and let's going to rerun it again.
I have a question as well.
Yeah.
But before that, it's regarding my 3-point rectangle, because every time I click on that, it doesn't show a rectangle.
My 3-point rectangle, because there will be a problem. The projection here, you will have it in red, or maybe there is no projection here and you don't have a point 2. That's why try to modify the sliders of the point 1 and point 2. Try to modify those sliders, and then you can find the final rectangle for sure. Try to modify that.
Yeah, I
let
try.
me know. Well, this is still running here. Let's see if I am lucky and finds. Sometimes you see, even selecting the reading higher value, it is stuck here because it's still thinking that here's the best one and it's trying to modify it to find the solution. Let's see if I am lucky. And because it's also about luck, something that you are lucky, and then find this point and starting to play with this rectangle, because as soon as it finds that the rectangle is bigger, with this inbreeding option, this will stay here and not come back again here. That happened before. But since I'm not lucky this time, and I cannot find the solution. Sometimes it happens, guys. I almost there. That's why I need a lot of populations here. Let's gonna stop the solver, okay? The most important thing is that you understand. Hey, here we go, almost. It started to work, you see? I was almost there, but well. I need more optimization, but okay. This was Galapagos. So for the submission of this day, one part of the submission can be, for example, place different cons and show me how you have done the most optimal bounding box, or place some buildings and place some buildings, some plots in the area, and show the biggest building that can be showcased, that can appear here in this plot. Okay. There is one part more for the class of today. We are a bit delayed, and sorry guys, because this took me longer than I expected, to be honest. But let's going to do this very, very quick. I need you to go to this website. Plan Finder. This one. Okay. Come here. Plan Finder, what it does is a Rhino plugin that is a Grasshopper plugin, sorry, and Rhino also, that generate automatic floor plans. Okay, I was in a meeting with the founders of Plan Finder because last year it gave us a lot of problems, and Clara and Annalena can tell you for sure. But this year they have changed the algorithm, they can change the software, they have updated, and it's working way better. I have tested a lot in a lot of different computers, and all of them were working. So let's go to download. And let's going to click on download zip. Okay. You download the zip file. Okay. Let's go to the desktop. I'm going to save it in the desktop. Okay, where is my desktop? Here we go. Here's my desktop. Here's my file. 1 second. Let me like this. Right mouse button. WinRAR. Extract to Plan Finder DH. And this is what you need to copy. Okay. Where do you need to copy this? Right mouse button. Let's go to our grasshopper definition. Okay. File, special folders, components folder. Okay. Create a folder called Plan Finder, if I find it. Yeah. You can call it as you like, doesn't matter. And copy paste all the elements here. Okay. One important thing for both Mac and Windows user. Plan Finder DH, right mouse button, properties, and here should appear unblock. Click on unblock and click apply. Please, all of you do this with me now. Let me know if you have any problems here. Okay? Doing this.
Sorry, can you show it again, please?
Yeah. Go to the desktop. Plan Finder DH. Select everything. Copy. And paste. Paste where? In Grasshopper. File. Special folders. Component folder. Okay. Place it here. I create a folder called Plan Finder GH version 2, and I paste it here.
Thank you.
Okay, good. Now remember, Plan Finder GH, right mouse button, the file GHA, right mouse button, properties, unblock. I don't have it because I already did it. Unblock, apply. Okay. If for somebody this is not working today, do not worry. We can see it next week. And we have also another class. We have 2 more classes to make this work. Okay? So there is time. Good, guys? Good. So
I
if you
have a question again.
Yeah, Bianca.
You told us to choose block, but what is meant with block?
Here, Bianca, what are you using, Rhino or Mac?
Microsoft.
Microsoft. If you do right mouse button properties, you see? Now, what the? Okay. It should appear like
okay.
this. You see? Unblock,
Yeah.
apply. If this, maybe it doesn't
okay.
appear. Maybe it doesn't appear, Bianca. Depends.
No, it's there. It's
Is there? So if you don't click unblock, you will not have the program. Okay, so you need to unblock it. Unblock, apply.
Okay.
I'm lucky. I know I'm lucky because I was doing it in the desktop one, which is the one that I downloaded, and I didn't unblock it before. Okay, but for all Windows user, for sure. Mac user sometimes. And also in Mac, it's not called unblock. I don't remember the name, but it's called like other thing, but it's also there. You can see it. Okay, so you need to tell your computer that this is a save file. Okay, so now guys, we save the rhino, save the grasshopper, close the grasshopper, save the rhino, close rhino. Opa. Yeah, if I am able to do it. Good.
I have a question as well.
Yep.
Where can we find the unblock in Mac?
Is down also, Lisa. Can you share your screen?
No, I'm on another device.
Okay. So it's down. Do you have also like unblock or allow? I don't remember exactly. Preparation. 1 second. Preparation classes, files. Close and open Rhino. So I'm opening again. If some Mac user can share the screen, I can tell you the menu where it was. Okay, here I open Grasshopper. And then I'm going to open this one. Okay, good. So guys, if you install the plugin correctly, you will have the plugin installed. How to notice? You need to go to P, or you will have a plan finder icon, and this is the plugin. Do you have it?
Can you show again where it is?
Yeah, under P in the Grasshopper menu, P, plan finder. And here you should have the plugin. The plugin is super simple. Do you have it? Do you have it or not? No one writing in the chat. Guys, do you have the plugin? Can I continue? Yara has the plugin. Can I continue? Sasha has the plugin. Xiao has the plugin. Okay, I'm going to continue. And Julian also. Cool. So first thing you need to do, log in. Okay, licensing your plugin. Click on licensing here, activate. Okay, and then full name. Write your name, the name of some of your relatives, whatever you want. Okay, you have a 30-day license. 30 days, by the way, guys, remember this, 30 days. If you leave this is going to be part of the final submission. If you don't do this in advance of the final submission, and you leave it for the end day, because final submission is going to happen in March, you will not be able to do it. And you will have to, I mean, I think that if you can change the email address, it'll work, but I will suggest, come on, let's do it before, okay? Put a panel with your name, Javier Fuentes, for example. Just put a panel with my name here, connect it here, connect. I am not going to do it because my license is already active and I am running the thing. I already did this, okay? Put a company, the company, we can put, for example, KIT or KIT, and put your email address. Javier.fuentes@kit.edu and connect it here. And connect it here. Then this component should become great. And you have the license activated. Let me know if you have problems. No issues, guys? Licensing work? No issues? This thing with 3 is not working. Guys, all good here? Can I continue? Okay. Sasha, is working for you? Yes? If there are issues with the licensing or with the plugin, don't worry. We can see it next week after class. Okay, after the lecture, I will be there. We can see it in presence there with all of you. Okay, and also prepare a bit the final submission. This is also why we are meeting in person right now, because then the last day, because it's like more efficient. So guys, what is the aim here? Let me explain you how this plugin works. This plugin has a component called plan fit. It's super easy, okay? Plan fit is this one. Plan fit, okay? Plan fit requires the next things. B are boundaries as closed curve, okay? E are the entrances of the houses. F is where is the facade, okay? Those are the housing units, okay? And then BE is number of beds, amount of beds, okay, that you want per house. And then some fit settings that you can use with the fit settings component. DS, downscaling, and US. You can downscale from 0.6, from 0 to 1, and upscale from, here I put from 0 to 10. Okay, so it's a matter to play a bit with the final result. The importance is here, guys. Every single house has to be grafted, and I also simplify it. We are going to do this in Rhino, okay? You put when I will explain this properly in the final submission, but the idea is you have your final building, okay, which imagine is, this case can be, this is mine, or later I can use this one if you want to try, okay, for you to see that it works also. I think that I already did it here, okay. The intention is that you have to input houses. My recommendation is do the next thing. In Rhino, create 3 layers, facades. Let me 1 second. That's going to hide all of this. Why I can't see my thing? Okay, well, I can do it like this. I am going to have in Rhino housing units, entrances, and facades, 3 layers. Okay. House units are rectangles that represent each one of the houses. Of course, they need to have one edge in common between both rectangles. Okay. In this case, I have 1, 2, 3, 4 houses. In this case, I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 rectangles. Okay. House units. Then entrances. Entrances, guys, I'm going to show it together with the houses, are lines that represent where is the entrance, where can be placed the entrance of your house. Okay? And then facades are curves also that represent where is the facade in your house. And as you can see, are different. I put 3 geometry components and do right mouse button, set multiple curves. And then, but the important thing is, guys, and this is really important for this to work, you have to select the curves in order. First, second, third, fourth. Entrances, the same. First, second, third, fourth. Facades, the same. 1, 2, 3, and 4. If you do it the other way around, you are going to receive an error and it's not going to work. Okay? You need to graph everything and then simplify it. Okay, good. Then the number of beds. What I did here is I use something that is called gene pool. Gene pool is part of, this comes by default in Grasshopper. You have it here. Galapagos is under the tab params, Galapagos. So here you have the gene pool. Gene pool is just numbers, okay? It's like number sliders that you can select the values. Okay, exactly like a normal number slider. Okay, if you do double click here, you can select the input. For example, in my case, how many houses do I have? 1, 2, 3, 4. So to select the number of beds, I need 4 numbers from 0 to 3. Okay, so I select. The gene count is going to be 4. Okay, decimals 0. I don't want decimals. And then the minimum value is 1, and maximum is, for example, 4 rooms. Okay, 4 beds. Beds equals rooms. Okay, so I have this gene pool. Okay. Then out of this gene pool, I connect this gene pool with the number, but the number again grafted. So the input to plan fit has to be always a 3. Check the structure. 2, 3, 3, 3. Check it. Okay, this is the structure. And then here we go, and here we have an error because I put too many, maybe too many here, too many here. Yeah, this is too big. Yeah, 2 is the maximum. Maybe in the first one I can put 3. yeah, in the first one I can put even, no, 4 is not working. 4 is coming back again to the initial. I can put 3, you see? Now what I do is connect the plan fit, okay? And plan fit generates different plans, okay? Different grasshopper plans. I can select in the option, I think. You see, you have different options. In this case, 1, this is the number 0, number 1. I'm gonna get number 0, and let's see what I have. You see, out of here, you should have different options that you can select with a list item. If I select the number 0, I am selecting the number 0 for all of them. Okay? So I can click later and put a deconstruct plan, which you have it here, deconstruct plan. Okay, and connect your plan here, and you can see what is going on. Okay, guys, any question till here?
Yeah, one question.
Yeah, Nelly.
Is the explanation for the final submission, because we don't have to do it right now, right?
No. You don't need to do it right now, Clara. I am just explaining how to do it. Nothing else. Okay. The final submission is going to be. We have one class specifically for the final submission and to review all of this together, and I will explain you what you have to do with this. But you don't need to do it now. What I'm just saying is, please don't leave it for the 1st of March. This task, because then some of you will have no more license activated. It's true that changing here the name, the email, the company, you can reactivate the license, but sometimes works, sometimes it doesn't work. What the guys from PlanFinder recommend me was, look, tell them to do it 30 days before or purchase a license. But purchasing a license, of course, I told that is not, we are not going to purchase the license because we are not doing this like a regular architectural office. And, so, okay, Kiara, it's just
but
no
option. Will we reconstruct this in a class, or do we have to do this at home?
What do you mean with reconstruct this?
Like the definition, usually we do it in class, but now you already have it and just show us. So do we have to do it at home?
Yeah, you have to do it. Yeah, you have to do it. But you can do it with me, right? It's just, I just had it before. I didn't do it with you because it's 1, 2, 3 components, right?
Okay.
Okay. The idea is that you were doing it with me, Chiara, and check if it was working for you. But anyway, you have the video. I'm going to upload it and you can redo it. The deconstruct plan, when you do the deconstruct plan, here you see that the number of bets that you enter, for example, for the first one, which is this one, I entered 3, and I have 1, 2, and 3 with this configuration. I can modify that, put 2, and then I have a different configuration. You see, I have a living room here. I have 2 bathrooms, and the beds are here. I can have maybe 4. With 4 doesn't work. Maximum is 3, I think. I can put 1. With 1, do a very weird thing. You see how weird is this? Put like a wardrobe at the entrance. Bathroom, bedroom, a small bathroom here, and then the living room. You can see that it's doing weird stuff, but it's really easy. Next thing I'm going to show you Finch, which is this tool, but way more advanced. But this is only available through purchasing, okay, through a payment service. It's a payment service. So, okay, one thing, guys, under the deconstruct, when you deconstruct this, you have the interior walls, the exterior walls, the doors, the glass window frames, furniture. You have a lot of stuff here, you see? You can select them individually. Okay. What you can do for the final submission, I will explain this in detail, but you can bake this geometry one by one in different layers in Rhino to later generate the presentation, and print them. Because in the final submission, I will ask you to generate different automated floor plans for one selected floor plan. And this works here and also works here. I did the same. I just copy paste my definition. Okay. And I have it like this. Let me select another option, maybe this one. Okay. I didn't specify here number of beds. You can leave it on -1, and this will automatically assign the number of beds depending the area. So for the biggest one, you will have 3. For the smallest one, you will have 1, or even one that is, like a studio. And again, with the deconstruct plan, you can deconstruct the different layers and bake them into your Rhino file. And you have also deconstruct room to calculate the areas of each room, interior boundary, function. The function, I think that should be like a text, right? Yeah, storage, bath, bed, circulation. You see, and you have like polyline curves that can be assigned to areas. And then you have the different areas for the storage, for the bathroom, for the bed. Bed means room. Okay, guys.
Javier, one thing. You wanted to explain how to draw icons on the components.
Display, draw icons. Okay, display, draw icons. But this I already explained it at the beginning, but it's under display, draw icons. And then you have the icons of the components, like me. Okay? With everything. I mean, if I don't do display, draw icons, I see things like this. Display, draw icons, it's like this. Guys, it's clear. Sorry, because today I know I took very long. But yeah, I wanted to explain you all of these points, and it was a bit complex with the Galapagos, but I hope that it was clear. Where's my definition? Here we go. Clear the definition with the plan finder component. Next week, we are going to work with Finch a little bit, and I will show you a little bit of Finch and how it works. Okay, also in the presentation. Okay, and what you can do with this. Okay, which is it's a similar tool for generating floor plans, but this works in 3D. Is more complex and more developed, let's say. Okay, we will talk about this. Any other questions? No one was clear?
Yes, the submission for this week. So is it now to create different floor plans or to create different geometry?
My suggestion is for this week, divide the row into 2 parts. One part, work with Galapagos, for example, with different cones, with different bounding boxes and different areas, okay, different plots for buildings, okay, and different buildings for those areas. And another one, generate floor plans. And the other part, the other half, generate floor plans for different housing units for you to practice for the final one. I will like, guys, that you practice this before next class. We can come to next class. We will be all of us in Fritzhalle Hörsaal, okay? And will be good if we can check that for everyone this is running. Okay, this is my suggestion. Otherwise, we can meet also in 2 weeks again, because we have the explanation of the final submission there. Okay?
Can you maybe show the whole definition again in Grasshopper once?
Is this, Nelly? Is this?
Thank you.
It's not very difficult. You're welcome. This is why didn't do it with you as usual, guys, because it's just 4 components. Okay. You have here the names. You just need to copy the same process and the input. This is the important thing. Remember, this is the important graft. If you don't graft, it's not going to work. Okay. Also the numbers. These numbers, you can use a gimple, or you can use number sliders and put all of them together and later graph as you like. Okay? Clear? No more questions? I'm gonna stop recording, okay? Pause, stop recording.